Okay, so I am going to do the simple beam problem that is in the PowerPoint entirely from the beginning to the end, trying to show you how we're doing it. And if I actually go all the way back up in the PowerPoint presentation, it starts with this slide right here. We are going to have to sum all of the forces in the x direction to make sure that they are all balanced and equal to 0. If they do not equal 0, that means that the beam would move. I am going to sum all of the forces in the y direction and make sure that they are equal to 0. And then I'm going to do all the torques or moments around a point, and that's the key. Choose a good point. So you're going to see me write these symbols on the paper as I go down and do this problem. The problem is down here and starts with having an 18-foot beam that has a uniform load of 1,090 pounds per feet. Beam starts as an 18-foot beam. So from here all the way over to here is 18 feet. The load was 1,090 pounds per foot. So it's a uniform load. So if I want to draw my reaction forces or my forces, I have force A going up here, and I have force B going up here. Sometimes people write RA and RB because those are reaction forces because they're holding it up. And then across this beam, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have 18 forces, and each one of them is 1090. So that's how you initially process like what the beam looks like with a free body diagram. At this point, I have to summarize or sum all of the forces in the x direction, and I do not have any forces in this free body diagram that are acting to the left or to the right. So that is 0. It's going to be 0. There's nothing to do with that. That calculation is done. I am going to sum all of the forces in the y direction, and that also has to be equal to 0. So as I go to sum those forces, I have force A, which is a positive number because it's acting up, and on a graph going up is positive. I have force B, which is a positive number because it's going up, and going up on a graph is a positive number. And I am going to subtract all of those. So to subtract all of those, so I'm actually going to go plus, and I'm going to take 1,090 pounds per foot times 18 feet. Because that's going to give me the overall weight of the beam. Positive force, negative force, because all of those are acting down. So when I do 1,090 times 18, I get force A plus force B plus minus 19,620 pounds. And the reason that's negative is because it's acting down. The foot and the foot would cancel, and this is still all equal to 0. So a little bit of algebra would allow me to say 19,620 pounds is equal to force A plus force B. And at this point I'm stuck because I don't know what force A or force B are. Logic would conclude that if I take half of this number, that's force A, and if I take half of this number, that's force B. And that would be a really good guess because this is a uniform beam. See where I'm going with that? If it's uniform, half of the load goes to A and half of it goes to B. But let's do the problem the right way. Let's not just guess and go to the end. If I don't know how to solve for A or B, I'm going to leave a little room, and I am going to sum all of the moments around a point, and the point I'm choosing is A. Which means this is going to be my pivot point. So all of these things, when I summarize them, still has to be equal to 0. And that is force A, which is positive, times 0 feet. Because force A is right here, and it is 0 feet from my pivot point. Then I'm going to add to that, because I'm supposed to be summing, force B, and force B is at the 18-foot mark. It's a positive value because it's acting up, and it's 18 feet away from my pivot point. You can put the pivot point, by the way, wherever you want. I am always going to put it at point A because I think that's easiest. And for my overall uniform load, we assume that the uniform load goes right through the center of gravity, which would be at 9 feet. So that is going to be I have to add it because we're summing these, but it is negative 19,620 pounds. It's the same number that I had right there. It's negative because that would be acting down, and that acts down at the 9-foot mark. So I'm going to do a little bit of quick math here. When I did my quick math, these two numbers multiplied together is 0. So effectively what I've done is I've eliminated a variable. I no longer have point A in my equation. B times 18, I can't do anything with that because I don't know what B is. But when I multiplied those two numbers together, this is what I get. And the units would be pound-feet. So now some algebra will be positive at this point if I move it to the other side by adding it to both sides. So I'm adding this number to both sides. Equals force B times 18 feet. And I can continue to solve by dividing both sides by 18 feet. And when I divide by 18 feet, the feet are going to cancel. So if I take that last number that I had and divide by 18, I get force B is equal to 9,810 pounds. So that's what B is, which happens to be exactly half of that. So now I can come back up here. If I know force B is 9,810 pounds, I definitely know that force A is 9,810 pounds. So I have now identified what force A and force B are, and I can finish this by doing a quick little diagram on some graph paper. I have set my graph up already, and here is my 18-foot beam, and I'm just going to go on a magical little journey across that beam. I know that at the start of the beam right here, that the reaction force right there is 9,810, because that's what I calculated it as back here on this paper. So every time I go 1 foot across the beam, it loses 1,090 pounds. So there's my first loss of 1,090. There's my second loss of 1,090. And every time I go a foot across the beam, that's how much I'm going to lose. And on my third, fourth, fifth, sixth, seventh, 8, 9, and right there, this is where I'm crossing the center point of my beam. That's the 9-foot mark. And then this just keeps going. 2, 3, 4, 5, 6, 7, 8, 9, and this should be the end of my beam, and it is. So this side represents all of the load going to A. This side represents all of the load going to B. And this is where the beam would break, where it crosses that center line. As I walked across the beam, remember every foot was 1090, 1090, 1090. This is where the beam would break. And that should make sense. If we have a beam support at both ends, it's going to break in the middle because this is a uniform beam. If I want to figure out the max moment at that point, the torque at that point, to do that, you just simply calculate the area under this curve. That is the easiest way to do it. The PowerPoint shows you a crazy way and stuff. And to calculate that area, that is a triangle. It's 1/2 base times height. 1/2, half. 9 times, in the height, 9,810 pounds. And that's feet. So the max moment, the max torque on this beam at that point is taking half times 9 times 980, 4, 4, 1, 4, 5 pound-feet. Now, in the PowerPoint on the computer, if you go back and look at that, the next page does have the answers. There was my reaction at both sides, and this diagram happens to be the diagram that I have right here. And then the next diagram is showing you that max moment. In the max moment, I calculated as 44145, and on my paper, when I calculated the area under the curve, I have 44145. So this is the simple beam calculation. The calculation that you are going to do for number 1 and number 2 are very similar. As a matter of fact, your number 2 is exactly like what I just did.